So today we are continuing our discussion of statistical inference. Remember, that's the process through which inferences about a population are made based on statistics, which we get from a random sample of data drawn from the population. Okay, so just keep in mind, the whole goal here is that we're trying to find the parameter of a population. Okay, and it's a parameter that we do not know already. And we showed you this before, just a quick reminder, we have a population, we're going to take a sample, giving us some data, we're going to calculate statistics, and then we're going to try to infer back to the parameter in question, okay? And that is the whole point of statistical inference, is to make that inference towards the parameter. So there are two ways we can do this, remember. One is hypothesis testing, and the other is confidence intervals. We've talked about confidence intervals last week. Hopefully you've done the homework and you watched the videos, etc. You literally can't learn enough about those, okay? Watch as many videos as you can have time for. Do the homework, think it over. Super important, and it's something that's going to keep coming back to us the rest of the year. You're going to learn how to make 5 different confidence intervals by the time this is over, okay? So, and they all have basically the same format. Same general rules, there'll just be slight differences. So the sooner you learn kind of how that works, the better off you'll be moving forward. But today we're going to focus on hypothesis testing, the other half, okay? And remember, hypothesis testing is used to assess the plausibility of a hypothesis about a parameter using a random sample from the population. Okay, so someone's going to make a claim about a population parameter, and then we're going to test to see if that claim is true or not. Okay, that's going to be our goal. Remember that confidence intervals were a range of values used to estimate a parameter based on a random sample from the population. So both of these are based on a random sample, okay? Which is important because that ties into our sampling distribution unit, because we're going to want to make sure that that sample comes from an approximately normal sampling distribution. So we're going to have those conditions that we have to check, you know, the random sample, the 10% rule, and the n times p and the n times 1 minus p rules. So all that will be a part of both of these. Okay, that's one of the parts that overlaps between these two. Just a quick review of confidence intervals. Before we get started, we did this one together in our last meeting. But this is the Gallup poll of adults 18 years or older. They sampled 1,000 people. And then of these, 37% said that football is their favorite sport to watch on television. And then we just constructed and interpreted a 95% confidence interval for the true proportion of people whose favorite sport to watch is football. And remember, when we're doing a confidence interval, there's a mnemonic device we can use to remember the steps, and that's the word panic. Remember, P stands for the parameter and the proportion we're talking about. So we just say something like, we're trying to determine the proportion of adults 18 and older whose favorite sport to watch on TV is football. Our best guess is 37%, but we know that every time we take a sample, we're going to get a little different result. So 37% is probably not the exact answer, so we create an interval. Then the next part was A, which is assumptions and conditions. You have to check those 3 things: that they took a random sample, that the sample is less than 10% of all adults, and then you have to check that n times p and n times 1 minus p are both at least 5. And they are in this case. So then we can declare that therefore our p hat will be approximately normal. And that's all from the previous unit with sampling distributions. Then the n stands for naming the interval we're going to create, and that's just a 1 proportion z interval. The I stands for the actual interval itself. And remember, you're going to use your calculator to find that, okay? And the command you use that you're looking for is just the name of it, 1 proportion z interval. I'll review with you later where we find that. And then at the end, the C, that's conclusion. We have to make a statement like this: we are 95% confident that the true proportion of adults 18 years and older whose favorite sport to watch on TV is football is between 34 and 40%, okay? Excuse me. So that was a confidence interval. That's what we learned or talked about last week. Hopefully you're familiar with that and you've tried some problems, etc. If you have not yet, you should go back and watch the videos, okay? So that's how we would estimate a population parameter. What we're going to do, though, now is learn all about what we call hypothesis testing, okay? This is very related to confidence intervals, but it has some differences. We're going to jump in and just do an example. I'll show you how this works. So, for instance, the CEO of a large electric company claims that 80% of his 1 million customers are very satisfied with the service they receive. Now, if you were in Texas right now, I don't think you'd be that high a percentage of satisfaction, right? But anyway, to test this claim, a local newspaper took a simple random sample of 100 electric utility customers. Of the 100 customers in the survey, 73 of them said they were very satisfied with the service. So my question is, does this data provide convincing evidence that the satisfaction rate is lower than the CEO claims? So this is how a hypothesis test gets set up, okay? There will be a claim about the population parameter. Someone will say, hey, I think the P is this. In this case, this guy is saying it's 80%, all right? A newspaper thinks, you know what, I don't think he's telling the truth. I think the real percent that's very satisfied is less than 80%. So the newspaper goes out and takes a sample of 100 people and finds out that 73 of them are very satisfied. Okay, so now the question is that evidence that the CEO might be misleading you? Okay, that the real percentage of people satisfied is maybe less than 80%. Okay, so this is the setup for a hypothesis test. Okay, there will be a claim, and we're going to test that claim by taking a sample, and then using our information and knowing what we know about sampling distributions, we'll be able to figure out if that claim is accurate. Okay, so that's kind of the goal here. So in all of these problems, there's going to be a claim. Okay, so the CEO makes a claim, 80% are satisfied. Then there's going to be another claim, or someone's going to suggest an alternate reality, okay? And the newspaper said, I think it's less than 80% that are satisfied. So it's kind of like a fight, who's right, okay? So when we do a hypothesis test, we have to state the hypotheses in the problem, okay? Which is kind of, we're stating what the 2 points of view are, okay? And the two hypotheses we create are called the null hypothesis and the alternate hypothesis, okay? And we denote the null as H with a subscript 0. And that's the claim that's made by someone, okay? That's what we think is true, all right? In this case, that's the 80% statement that the CEO made. The alternate hypothesis, denoted as capital H with a subscript A, that's called the alternate hypothesis, okay? And that's like what the newspaper is trying to show, that the newspaper thinks it's less than 80% that are satisfied. So to start a hypothesis test, you need to list out these hypotheses. So the null is the suggested parameter value that we assume to be true. And then the alternate is what we believe may be true, or what we're trying to prove based on our sample data, okay? So this is how you would write it. And this is specific to sampling proportions, okay? They'll be different when we do sample means later. So we'd say the null is that capital P equals 80%. Remember, P is the population parameter. That's the symbol for that. So the null is whatever they claim the percentage is, okay? Something to note, the null is always equal. So you'll always put an equal sign in there for that, okay? And we run these hypothesis tests based on the assumption that whatever claim is being made, we believe it, okay? We think it's true, all right? We assume that this guy is telling the truth, okay? But we make an alternate hypothesis, and this is what we think might be happening if the guy is not telling the truth. So we say, in this case, the newspaper thinks that it's actually less than 80% are satisfied. So we write capital P is less than 80%. Now, the alternate could be any of these three symbols. It could be less than, it could be greater than, or it could be not equal to, okay? And all of those are dependent on the question in hand. And you'll be able to tell just by reading the question what they want the alternate to be, okay? It's pretty obvious in this case because the question said, does this show evidence that less than 80% are satisfied? So we're trying to show less than 80%, okay? Notice nowhere in either hypothesis do I mention P hat, okay, the 73 out of 100, which was 73%. That is not mentioned, okay? We do not want, we do not use the sample at all in the null or alternate hypothesis. So whatever number you put in the null, you're going to also put in the alternate, Okay, so that's super important. We use the same number in both cases. So null is always equal. Alternate could be one of those three. It'll all be based on the question that you're given, okay? Now, after you write the hypotheses, the next thing we're gonna have to do is check the conditions or assumptions, okay? What we really hope is that the sample that we took, of those 100 people, that they're a part of an approximately normal sampling distribution, just like we did in the previous unit, okay? If we can, draw a bell-shaped curve that sample is a part of, then we can use z-scores to find out the probability of getting the sample that we got, okay? And we'd really like to be able to use that tool, okay? So without these conditions, we can't use a z-score. So that's why we need to check these. So it's the same three conditions from before. It's the same three from the confidence intervals. It's got to be a simple random sample. Got to be can't sample more than 10% of the population, which we're super good there because 100 times 10 to be 1,000, and that they said the population was 1 million, so we're really good. And then the third thing is you have to check that n times p and n times 1 minus p are both at least 5. And the p was 80%, so the 1 minus p would be 20%. Both of those end up to be 80 and 20. They're both bigger than or equal to 5. Okay. One thing to notice here, we are actually using the null hypothesis. Okay. Whatever claim they make, we believe that that's the p. So that's what we use in that equation. Okay. In confidence intervals, if you remember, we actually used p hat for that value because that's all we had in a confidence interval. Like we didn't have a claim of what we thought the proportion was. All we have is the one sample we take. So we assume that sample is a pretty good estimate, okay? So that's one difference between confidence intervals and hypothesis testing. In hypothesis testing, we use the null as the p, okay? So all those were true. So therefore, we can assume the sampling distribution the sample is a part of is approximately normal. And that, of course, opens up our use of z-scores, which obviously we're going to want to use a z-score for this, okay? So, since those three conditions were met, we know this. The mean of the sampling distribution will be equal to p. So I can draw this bell-shaped curve, and I can put p in the middle, okay? And that's the null, remember, so we believe it. Then I need to find the standard deviation. Remember, we had this formula. So I plugged in the numbers, 80, 20 over 100, took the square root, and I get 4%. So that's the standard deviation of that sampling distribution. Okay, that's how I got the 80 and the 4%. Now what we do is we take our sample proportion, our p hat that we took, and we see, where does that sit in this distribution? Okay, and what we usually do, since this one was, the alternate was p is less than 80%, we put the 73% on the left, and then notice we shade to the left of that 73%. So we're really just trying to figure out what's the chance of getting 73% as our sample, knowing that we think the population parameter is really 80%, okay? And kind of the whole point of this activity is looking at that sample and deciding kind of where it falls, okay? If that sample ends up being someplace really close to the actual proportion, the 80%, then we're probably going to believe the claim, okay? I just put a couple lines on the graph there if you're watching. If the sample ends up to be, someplace way off in the edges, that means maybe that the claim is not true. Because if the claim's true, our sample should be pretty close to the middle. It should be pretty close to the actual parameter. So that's what we're trying to figure out. Is 73 close to 80? Is it close enough to say, yep, it's, I could still consider it 80%? Or is that 73 really far away from 80? Which would make me think that the 80 claim in the beginning was not true, okay? So basically, if we think if the claim is true, we expect a sample to be really close to the claim. If the claim is false, we expect the sample to be further away from that parameter, okay? So that's kind of the thinking behind this. So then what we do, basically, is we use a z-score to find out what is the percentage of the time, or the percentage of that red area from the 73% sample and even lower, okay? So we would use a z-score, and I showed the formula here. Remember, our z-scores, we're usually used to x minus the mean divided by the standard deviation. And in this case, instead of x, it's just going to be a sample, the sample we took, minus the null hypothesis, and then we divide by the standard deviation, okay? So in our problem, though, if you just use the picture, it's 73 minus 80 divided by 4%, okay? Just like our old z-scores. So I end up with a z-score of negative 1.75. And then I can use that using the normal CDF command, and I would use negative 10 to negative 1.75 to find that red area. And I find out that that red area is 4%, okay? That 4% has a special name. It's called the p-value. And basically what it means is there's a 4% chance of getting 73% or less people saying that they're satisfied with their electricity company if the real percent is 80%, okay? So if the real population percentage is 80% are satisfied with their electricity service, then there's only a 4% chance of getting a sample of 73% or less that say they're satisfied. So there's not a very good chance of getting this sample, okay? Only 4 out of 100 times would this happen, that I get 73% or less satisfaction, okay? So when that percentage is low like that, it really is telling us that, hey, you know what? I don't think that 80% is probably accurate, because we should have got a number for our sample much closer to 80% if that was the real number, okay? So that is the thinking behind the hypothesis test. If that percentage, the red percentage, that 4%, if that had been like, 50%, then, that's a really high chance of getting that sample with that mean. So that would be evidence that the 80% claim is probably true, okay? So it's all based on how much that red p-value ends up being, okay? That's why we use the 80% as the mean when we make the z-score calculation, okay? That's why this is here, because we believe the null is true, okay? We do this whole problem thinking it's true. And so that p-value is a super important part of this, so we're going to talk about that for a second. This is a definition in purple that you need to memorize, okay? Like literally word for word, you need to memorize it. It's going to be on the AP test for sure. It'll be on a multiple choice question, and usually they put it in some part of a free response question as well. It's kind of central to the whole idea of statistical inference, okay? So the p-value is the probability of getting the sample we got or a more extreme result given the null is true. Okay, I'm going to say it again. It's the probability of getting the sample we got. So remember, the sample we got was 73%. Or a more extreme result. And more extreme means like further away from the mean. So that's why we shaded that picture. If you remember, we shaded it to the left. Or a more extreme result given the null is true. So we assume the null is true when we make that calculation, okay? I'm going to back up. At the very end, we decide if we agree with that or not, okay? So if the p-value is small, it suggests that the null may have been incorrect, okay? That our sample that we took might have come from a population with a different parameter. In this case, we would think the parameter is probably closer to 73%, okay? If the p-value is large, it suggests that our sample comes from a population with a parameter that the null suggests. So the higher the p-value, the more likely the null hypothesis is true, okay? And the smaller the p-value, the less likely it's true. And notice I keep saying likely and less likely. This is not definitive, okay? Like at the end of this, we can't say for sure either way if the null is true or not. What we do is we compile the evidence and kind of make our best inference, okay? So I'll keep staying vague statements because this is not 100% guaranteed we're going to be right, okay? We're just basing this information off the one sample that we took, okay? So just keep that in mind. We can compare the p-value. I've been saying, a low p-value means the null is probably not true. A high p-value means it probably is true. But what's the low and high? Like, how do we define that? Well, you can compare the p-value to a specific or specified level of significance, okay, to determine the accuracy of the null. And in these problems, they will tell you that level of significance, and it's denoted by the symbol alpha, which is like a sideways fish, okay? So that is the value that we would compare to the p-value, okay? It's kind of like a line in the sand where we say, you know what, if our p-value is smaller than alpha, that's when we start saying that the null is probably not true. And if our p-value is bigger than alpha, then we think that the null is probably true. So this alpha is super important because it makes the decision for us whether we believe or disbelieve the null, okay? And I know there's a ton of stuff in here that's totally new to you, and in a week or two, this will seem like super easy. You'll be comfortable. You'll have seen it so many times, it'll start to make sense. And keep in mind, the stuff you're learning now is we're going to use this the rest of the year, okay? So I know it sounds like French right now, but it will make more and more sense as we go, okay? So here's the deal. If your p-value is less than alpha, then we reject the null hypothesis, okay? And that's actually the terminology we use. We say we reject the null, okay? It means we don't believe the null. If that's the case, then our conclusion ends up being, because our p-value is less than alpha, we reject the null hypothesis. We have evidence that the alternate is true. Okay? Notice nothing definitive there. I just say we have evidence that the alternate is true. If your p-value is more than alpha, then we fail to reject the null. And again, that's how you word it. Okay? And if you think about that, we fail to reject. So we're not rejecting the null. So in that case, we tend to believe the null is true or accurate. Okay? And I know those sound super funny, but that is the wording that you have to use. You either reject the null in favor of the alternate, or you fail to reject the null. Okay? And this is one of those situations too where you have to memorize that wording. You're not allowed to whip out your thesaurus and find a different word for reject. Use this terminology, okay? Now, our conclusion then would be if we fail to reject the null, we say because our p-value is greater than alpha, we fail to reject the null. We'd say we don't have enough evidence to say that the alternate is true. So we're basically either saying, yeah, hey, we have evidence that the newspaper is right, or we're saying, you know what, I can't say the newspaper's right, when they're trying to prove that it was less than 80%. And again, this is going to sound so foreign to you right now, but it will make more sense as we move on. So this is how we would do. So if we use for this hypothesis test, let's say I said that alpha was 5%, okay? And that it'll say it right in the question in your future. So our p-value was 4%, which was less than 5%, right? And that's the wrong symbol. Haha. This should be less than, my bad. Okay, so we would say, because our p-value is less than alpha, we reject the null. And then our final conclusion would be, we have sufficient evidence to say that the proportion of satisfied customers of the electric company is less than 80%. Okay, so remember, less than 80%, that was the alternate hypothesis, right? If you remember. So we're saying, yeah, I have enough evidence that I think the real proportion was less than 80%. Okay, and that's because our p-value was less than the alpha that they asked for. Okay, we're going to get that one for right now. If we had used an alpha of 1% instead, okay, and this is the deal, it's kind of like confidence intervals. Remember, you could have 90% confidence intervals, you could have 95%, or you could have 99%. For hypothesis testing, you can have different values of alpha. Kind of the typical one is 5%. That's the one you're going to see the most. But they can choose different alphas. So if they had used an alpha of 1%, then our conclusion would have changed, okay? Because our p-value is greater than alpha now. So 4% is more than 1%, so now we would fail to reject the null, okay? So then we'd say we do not have sufficient evidence to say that the proportion of satisfied customers of the electric company is less than 80%. So you can kind of think of that alpha is kind of like our standard of proof, okay? The smaller the alpha, the more crazy sample I would need. I would need a sample further away from the claim to disprove it, okay? So an alpha of 1%, it's kind of like you're more sure of the answer when the alpha is 1%, okay? But usually we stick with a 5% alpha, okay? And that part will always be given to you in the question. So as you read the question, at some point they'll say, use a significance level of 1% or 5%. Or sometimes they even just say, use an alpha of 5%. And that's just letting you know what to compare the p-value to, okay? And again, this is going to sound totally weird until we do a couple. Here's just 3 examples I want to show you. This is kind of a terminology thing. Remember that the null hypothesis is always equality, okay? So in this case, whatever the problem was, they said the null was 50%, okay? Then the alternate, though, if you remember I said, could be one of 3 things. It could be less than 50%, more than 50%, or just not 50%, okay? And the interesting thing is, based on that symbol, that's telling you where the p-value is going to be located. If it's less than 50, the p-value is going to be over here. Okay? And we call that a left-tailed test. It's also called a one-tailed test because there's only p-value in one end of the picture. Okay? On the bottom one, when its p is greater than 50%, then the p-value is going to be on the right side. Okay, and again, this one's called a right-tailed, or we also call it a one-tailed test. Because again, there's only p-value on one side of the picture. But when they do the middle one, the not equal to one, then there's p-value on both sides. Okay, and this is called a two-tailed test. And the only thing that ends up happening on a two-tailed test is that we find one p-value, like let's say it was 3%, and then we double it. So that's like it's coming from both sides. So our final p-value would be just double that 3%. So that's just terminology. You need to know one-tailed test and a two-tailed test, like what's the difference. And it's just that alternate inequality, okay? If they're looking for less, it's one-tailed. If they're looking for more, it's one-tailed. If they're looking for just not equal to, then it's two-tailed. And how will you know? The wording of the question, okay? The question will specify, we think it's more, or it'll say we think it's less, or it'll say we think it's different, okay? So again, that's something you need to memorize and understand. So we're almost ready to do our first one here, like do one completely from scratch. Remember for confidence intervals, we had panic, remember? That was our mnemonic device. Well, for hypothesis testing, the mnemonic device is phantoms, okay? So you're either, on anything you do the rest of the year, you're either panicking or you're doing a phantoms, okay? And here's what the letters mean. And again, you could write these right on your piece of paper if it helps guide your answer. They're not necessary. You don't get marked wrong or right by having just the word phantoms on there. But I think it's super helpful to make sure you've included everything you need. The P stands for, just like it did in panic, okay? The P stands for state the hypothesis, the population and the parameter of interest. So like in our problem, we'd say, we're trying to figure out the proportion of electric customers who are satisfied with their service. So we'd say something like that. So just like in a confidence interval where we had to say, what's the population, what are we trying to find? The H stands for the hypotheses. That's pretty straightforward. So that's where you'd write the null and the alternate, okay? And we'll practice that. A is just like it was in panic. It's the assumptions and the conditions. So that's where you would run through the random sample 10% rule and the n times p and n times 1 minus p thing. Then N in panic, remember, was name the test or name the interval. In phantoms, it's name the hypothesis test. So for us, it would be a 1 proportion z test. And remember, for confidence intervals, it was a 1 proportion z interval. Okay, So you have to name the test. And then T, you have to tell the test statistic, which means you're going to have to tell us what the z-score is. Okay. Remember, we calculated a z-score. I showed you how to do that in this example. The cool thing is you do not have to show the equation for the z-score. You may let the calculator calculate the z-score. So all you have to do is report it. Okay. There's nothing. You don't get extra points for showing the formula. You can actually lose points if you do something wrong with the formula. So really, to be safe, we just want you to report the z-score. Okay, and I'm going to show you how to get it on your calculator. The O stands for observe the p-value. And by observe, I really mean state it. So as part of this, you're going to specifically say what the p-value was. Okay, remember that was the percent from the z-score. So those two things need to be stated right on your paper. Okay. Then we're going to make a decision. That's what the M stands for, and that's reject or fail to reject, and that'll be based solely on the value that they tell you for alpha. Okay? You'll look at your p-value, you'll look at the alpha, and you'll decide, am I rejecting the null or am I failing to reject the null? Okay? And we actually have to make we have to write a sentence where we say our p-value is less than alpha, we reject the null, or our p-value is more than alpha, we fail to reject the null. Like, we have to say that. And then the S is the state the conclusion in context, and that's where we're going to say, we have evidence that the alternate is true, or we're going to say we don't have evidence that the alternate is true. And we'll do that in context as well. All right, so, there are only 5 steps to make a confidence interval, but, there's 8 steps for a hypothesis test. I would say this too. On the AP exam, you're only going to have to do this one time, okay? You're going to learn how to do 7 or 8 different hypothesis tests for the rest of the year. But on the actual AP test, you will only have to do this phantoms thing one time, okay? From start to finish. So, we're gonna keep practicing this idea, etc. But just realize you're only gonna have to do this once on the AP test, okay? Usually one interval and one test, basically. So let me show you what a test would look like. Okay, and I actually wrote the phantoms on the side. That's optional. Okay, you don't have to write that. But this is from that same problem. So it says P stands for population and parameter. So it's electric utility customers is the population, and the parameter is the proportion of satisfied customers. Now, you can write that like that, or you could write a sentence and just say, we're trying to find the proportion of satisfied customers from the electric company, something like that. But you need to mention who's the population, the electric company customers, and what are you trying to find? The proportion who are satisfied, okay? Then you'd write the null and the alternate. So the P was 80% and for the null, and the alternate was P is less than 80%, okay? You can think of everything that's typed out here is the stuff you have to actually have to write on the AP test, okay? Then you move on to A, the conditions. So we have a simple random sample of 100 taken. The population is greater than 1,000 customers, and it's much greater than that, so we know we've satisfied that 10% rule. And then you have to show that 100 times 80 and 100 times 20% are both bigger than or equal to 5. Done. So then we say, therefore, the sampling distribution is approximately normal. So all that is part of the A. Then the N is name the test. So you just write down one proportion z-test. And then you would say what the z was, which was negative 1.75. And I put the picture here in blue, not necessary on the AP test. I just wanted to reiterate where we got that negative 1.75 from. The O stands for the p-value. Observe the p-value. So the p-value is 4%. And then we say because our p-value is less than 5%, we reject the null hypothesis. That's the make the decision part. And then the final conclusion, S stands for state the conclusion. There is sufficient evidence to conclude the proportion of satisfied customers at the electric company is less than 80%. Okay? So that would be a full and complete hypothesis test. All right? So, a couple things are to realize, this part is the same as the confidence interval. The conditions are the same as for the confidence interval. And we still name it like we did for the confidence interval. And then the stuff you have to learn are the hypotheses, getting the z-score, getting the p-value, and then making your decision, okay? Now, if you have a calculator near you or handy, why don't you take it out and turn it on? I'm going to show you how to do this on your calculators, okay? And this is how you would get the z-score and the p-value. So this is super important, okay? So, if you have your calculator out, the first thing you do is you hit the stat button, okay? And then you're going to move over from edit to calculate to tests, okay? Same thing we did with confidence intervals. And then a one proportion z-test is the fifth choice down. So I want you to choose that number 5, okay? And if you remember, the confidence interval for this was below this, right? It was letter A, so you had to go 1 through 9, then 0, then A. So the confidence interval will just be further down the list. Once you choose that, you're going to get this screen over here. Let me explain what all this is. The first line, P with a 0, that's the null hypothesis, okay? That is whatever the claim was, we got to type that in. So 0.80, or just 0.8 is fine. Okay, but you have to tell the calculator the null. And that 0 there is the same 0 in both spots, okay? Like this 0 and that 0 mean the same thing. They mean the null. Then you need to tell the sample that we took. And remember, just like with confidence intervals, they want it as a fraction, okay? So we had 73 out of 100 were satisfied. So over here, you have to write 73 and 100. Okay, you are not allowed to type in 0.73. Okay, remember that's illegal. If you type in 0.73 as the x, you'll get an error statement. Okay, so you have to do the whole fraction, 73, and then for n put 100. The next line here is the alternate hypothesis. Okay, so we either think that it's not equal to the null, we think it's less than the null, or bigger than the null. Okay, so there's 3 choices, and we obviously, the newspaper is trying to see if it was less than 80, so that's less than the null, so we'd choose that middle choice that's highlighted. Okay, then for the color part, your calculator may or may not have that option. This calc simulator I was using simulates like the highest end calculator, so your calculator might not have that, and that's totally fine. But then you have 2 choices for how you make this happen, okay? You have calculate or draw. And I've showed what happens when you do both, okay? If you choose calculate, you get the screen on the bottom left. And you can see it lists the alternate hypothesis, so you can double check that. There's your z-score, which you'd write on your paper. Here is your p-value, which you would write on your paper. And you can round the p-value to 2 decimal places unless it's really, really small, okay? Like sometimes the p-value can be like 0.0001. Then you would just write down those decimals until you hit the 1, okay? Be careful on p-values because sometimes the p-value will show up like this. They'll say 6.248 e -5, okay? That's scientific notation. Okay, don't say, oh, the p-value is 6.24. That's impossible. That would be 624%. What you would need to do is move that decimal 5 places to the left. So be very careful, okay? It may be so, could be so small that it's scientific notation. But that's where you'd get those numbers to fill into the test, okay? Right on your calculator. Like, you do not have to look those up yourself. Run the test on your calculator, get those answers. Copy them onto your sheet, okay? If you choose the draw command, then you'd get this one on the bottom, where it would actually draw a picture, it shades it in for you, which is kind of cool. And after it does that, it gives you the z-score right here and the p-value right here. And those are the only 2 things you need to know from this test, okay? Get the z-score, get the p-value. And you have to say those on the AP test or you would lose points. So that's why we need to do this on your calculator, okay? And there's videos of how to do this on your calculator also on the thing, in the notes and stuff. Now, I do want to show you one more thing. I know it's 12:42. We may go over by a minute or two. Just bear with me. I need to show you just one more thing quick. I just want to show you an example of that two-tailed test, okay? Down here where that P would not be, where we'd say not equal to, I just want to show you what happens. So it says large survey of restaurant employees found that 75% reported that work stress had a negative impact on their personal life. So a large survey, that's going to be their claim. Okay, that's going to be the null. Then it says the human resource manager of a chain of restaurants is concerned that work stress might be affecting the chain's employees. She asked a random sample of 100 employees to respond yes or no to the question, does work stress have a negative impact on your life? Of these, 68 say yes. So is there evidence to conclude that the proportion for this chain of restaurants is different from the value given for the national survey? And then it says alpha equals 5%. So this would be an entire, a fully informed question. Obviously, the 68 out of 100, that's the sample, right? But because in the question it said, is it different? That's why we do the not equal to. Okay, but it doesn't say they think it's less. They don't say they think it's more. They just say we think it's different. Okay, so that means that the alternate would be P is not 75%. Okay, and this is called a two-tailed test because when we do the test, we're going to have p-value on both sides. Okay, so let me show you what this looks like. Okay, the only real change here is that the alternate, we have to say not equal to 75%. We would still run through the conditions just like before. We would name the test. We would go to our calculators to get the z-score and the p-value. We'd have to be careful though, because when we say the alternate on your calculator, you have to choose that not equal to option, okay? And then basically this is what happens. The calculator says, all right, my sample was 68%, right? I'm up here in the picture now. That was my p hat, right? 68 out of 100. So the calculator figures out that p-value, okay? But because it was a two-tailed test, it duplicates that over on the other side. So it kind of pretends like they got the same result, but in the opposite direction, okay? So instead of being 7% below 75%, it includes 7% above 75%. And it's just the way it is with two-tailed tests. So whatever it finds for the p-value for one side, it basically just doubles it, okay? So down here you can see the calculator will find a z-score, it'll look up a p-value, 5%, and then it'll multiply it by 2 to get your final answer, okay? The calculator does all that on its own as long as you say that the alternate was not equal to, okay? Then our conclusion would be, or make a decision, the M, because our p-value is greater than 5%, which it is, it's 10%, we fail to reject the null. So we'd say there's not sufficient evidence to conclude the proportion of restaurant employees who are negatively impacted by work stress is different than 75%. Obviously, it's harder to reject the null hypothesis in these two-tailed tests because the p-value always gets doubled, okay? So even if the original p-value on one side was 3%, which would be less than 5, in the two-tailed test, it automatically gets doubled and becomes 6%, and then all of a sudden it's more than 5% and we fail to reject. So these two-tailed tests are harder to reject the null because the p-value always gets doubled, okay? Awesome, I'm only 1 minute over. So I know this is a ton of information, okay? If we were in person, we would have done this over 2 days of class time. But things are what they are. You gotta spend a little bit of time on this. I'd recommend watching a video or two that are in the homework. Do your best. I will be around to answer questions later today and all weekend. So I would not put this off. If you haven't done the confidence interval assignment yet, you can't put this off much longer. We only have 2 weeks left of the try. So jump in there, see what you can do, and ask questions if you have them, okay? Thanks so much, you guys, for coming and staying. I know it's not very exciting when you just listen to me talk, but unfortunately, these last 2 lessons, that's kind of the way it is. Have a great weekend, and I will see you guys next week.